to be on the channel specifically. I think we focused a lot, mostly on general geology. Please show your credentials as well, just so folks can know where you're coming from. And I'll stick this at this part at the beginning, so we can be like, here's Tony, here's his background, and then I'll stop recording and we'll sign off.
Okay, so I have an honours degree in mathematics and a PhD in geophysics, specialising in the modelling of sea level change and glacial isostatic analysis. I've got some qualifications in seismology as a result of those studies, and I've made a point of studying geochronological techniques and the physics of climate change and planetary atmospheres. As a result of public debates that haven't apparently resolved themselves in favour of people who know what they're talking about. But so that's where I'm from.
Welcome, PhD Tony. We have been trying to get this thing settled and scheduled for the longest amount of time. So it is my absolute pleasure that we've finally gotten it, and we're sitting here in the same virtual room.
In the same virtual room, that's right. Well, I'm very grateful for you having me on. Yeah, I've been having sort of serial migraines for ages and ages, so just sometimes check my email and things slip by. But we finally managed to schedule it. Only took however many months, but yeah.
Yeah, so, we've been leaping and bounding over both of our schedules and respective, sudden new things like migraines. I've certainly had things pop up on my end too, so it's nice that we're finally sitting here chatting. And Tony, enlighten me, what is it that we're going to be chatting about today?
Well, hopefully, I've actually got a fairly broad spectrum that I want to bring up, but my speciality is glacial isostatic adjustment, which is a little-known geophysical process. And it turns out that the rest of geophysics kind of regards what I do as noise, and they would like specialists like me to make it go away, please, so that they can analyze real signals that they're looking for. But the most important sort of physical manifestation of GIA, or the largest scale, is sea level change, and particularly paleo sea level change. So we have to date and interpret sea level indicators very carefully, and so there's a lot of crossover with geochronology, and so I'm hoping to start with some of the geochronology, some GIA, then the geochronological techniques that we rely on. But this also impacts on actually hominin migration routes and hominin habitation. So we might delve there, because that might be interesting to you and your listeners.
Yeah, we'll dip a little non-opposable toe into that pool, ideally. We'll get us started then. So maybe a couple of basic definitions of the work, like what it is. You say you're parsing through the noise. So what exactly causes this noise, and how do you, in your profession, manage to kind of tease away the confusion?
So, when you're looking at modern sea level change, for instance, you're trying to use satellites to very precisely monitor sea level change, but there's an ongoing signal due to the mass distributions due to previous glacial cycles. Similarly, there are actually perturbations to Earth's gravitational field. So there are missions around where we're trying to use Earth's gravitational field to detect modern day mass changes, but these signals are overlaid on top of glacial rebound, or sort of mass returning to underneath where the large ice sheets used to be. So people who are doing satellite missions, they tend to view this as noise. Like they're not interested in what happened 20,000, 6,000 years ago. They're only interested in what's happening now. So they'd like you to get rid of the glacial isostatic noise, so that they can actually work out what the modern processes are and isolate the modern processes. And so one of the ways we do that is we look at the paleo sea level record and see what we can determine from the paleo sea level record about these processes, and then extrapolate them forward. Unfortunately, it's not that simple. We don't necessarily have all the sea level records that we would need to do that. And in some areas like Antarctica, where there is significant modern mass change, there's actually an issue with very recent glacial events, significant glaciation in the last couple of thousand years, which has gone away, and that produces its own signal in addition to the sort of the last glacial cycle and the previous glacial cycles.
So correct me if I'm wrong, because this is new to me, so I'm hoping I don't butcher it too badly. But is the idea kind of that by figuring out how these mass changes occur sort of at the poles of the Earth with these glaciers, how they're changing with the precession of the Earth and its rotation through these natural cycles, that you kind of establish a baseline of what this signal looks like at any given time period, and then you can identify it when you're checking other potentially non-glacial areas? Is that kind of what we're doing here?
Yeah, that's kind of what you're looking at.
Please correct me. Tell me where I'm wrong.
No. You're surprisingly sort of right, and I'm hoping to actually discuss that, because the main data set we have for identifying these glacial cycles and the timescales on which they occur is the marine isotope record, the marine isotope stages, as they're called.
Right.
And we, and they, identify these large scale oscillations on, over quite long timescales. And that, feeds into what we're doing, but we're trying to be a little bit more precise than that. So we're looking at very specific sea level records in regions, and from the locations of those sea level records and their temporal characteristics, we can tell something about the geometry of the ice sheets, how long they were there, and the relaxation characteristics of the Earth. How thick is the effective lithosphere? What's the viscosity of the upper and lower mantles? And we can achieve some degree of separation between these parameters using these sea level records.
So how long they were there? Perhaps the time period that they might have been there. I see.
So obviously in a lot of this, there's a lot of very direct anti-Young Earth creation data. There's which makes me quite frustrated when Young Earth creationists assert what is plainly nonsensical claims, that they're just unaware of how we do these things, and that there are people whose job it is to determine what sea level has done for the past 140,000 years, for instance, or during the last interglacial. And so we can be fairly confident that there was no global flood at 5,000 years ago or whenever it was, because we've looked at the global distribution of data, and if there was, we would have detected it. There's a lot of just we can directly refute a lot of what they're claiming, because a lot of these processes simply can't be sped up. You cannot just hit fast forward on the evidence we have. You can't speed up glaciers. You can't speed up the formation of shoreline indicators or sea level indicators. Erosion of beaches. You can't speed that up. You can't speed up the transport of glacial debris. You can't speed up the erosion processes. And even if you could, we have data sets that can tell us, well, actually, that didn't happen. That wasn't sped up.
Right.
And I noticed in your discussion with Rebecca, I think, you had some mentions of cosmogenic exposure age dating. And that's something I'd like to discuss in detail today, because it really does drive a stake through Young Earth creationism. You cannot, this is a data set that cannot be explained by magical changes in isotopic half-lives or speeding up radioactive decay.
Well, because it would have to be that, wouldn't it? It would have to be straight up physics-breaking magic, because a lot of these processes that you were just referring to, and I know this just from my kind of more layman's understanding, kind of barely looking into some of these geologic processes, but a lot of this is dependent on things like the precession of the Earth, as it moves in its position in space. And so,
and we have data to demonstrate it. So
and so
exactly.
It's like, speeding up glaciation would be very difficult because these kinds of processes aren't just in relation to, temperature and pressure in its patterns and its rhythmic patterns here on Earth, but those rhythmic patterns are generated by Earth's position in space. So what you said about hitting fast forward, that really is what we would be doing, right? We'd be hitting the little, fast forward button, and the Earth is zooming, faster than anything else, violating its gravitational norms in order to get these, in order to fake these signals, which is quite strange.
And so the entire solar system has to speed up in order for the gravitational perturbations from the Jovian planets to drive the Milankovitch cycles. You would need to speed up the entire solar system, to get the precessional, the obliquity, and the ellipticity perturbations that combine to drive the glaciations that we observed for the last few years. But even beyond that, I would suggest that the snowball phases of Earth's history, which was another thing that I wanted to sort of talk about, there are these massive snowball phases where you get runaway glaciation because albedo cools down the Earth. It reflects all the light. It reflects all the light from the sun. So if you start getting an ice sheet, it'll cool down the Earth, and then you'll get more ice. And in a couple of phases during Earth's history, there have been the Earth seems to have been covered with ice. And in the Huronian glaciation, that was perhaps I think the evidence is that even the oceans were covered with sea ice, and we only got out of that because of carbon dioxide emitted by volcanoes.
Right.
But there are more recent glacial periods, cryogenic period, where there have been quite substantial glacial deposits, and the question then is, when did this happen in the Young Earth hypothesis? When in the Young Earth hypothesis was Oman glaciated? Because we have evidence of glacial deposits in Oman. You would think that if that was something that occurred on a biblical timescale, someone in the Bible would have noticed. We can identify, up to 2 kilometers of glacial deposits in Oman. How quickly do you think glaciers form? How quickly do you think they can develop these 2 kilometer thick layers of debris? And and however long you think it is, you need to double it at least, because there are at least two of these phases.
These would be post-flood glaciations, according to them. Yes, these would be.
Well, the more recent glaciations must be post-flood, but these glaciations they could claim are pre-flood.
Okay.
But even so, you've got these very, very thick, hundreds to thousands of meters thick glacial deposits, on top of which you've got tens of meters of carbonation capstone, and then hundreds of meters of subsequent. So how long is this period? How quickly, you've got to get rid of you've got to build these glaciers, leave them there long enough to generate a kilometer's worth of debris, and then do the rest of the stuff. And if you're trying to claim that, well, Oman is only one place, no, we can prove that this happened in Brazil, in California, in Canada, in Greenland, in Australia, in Namibia, in Svalbard. We can find these deposits all over the place, and they date to the same. They date the same wherever we've got volcanic tuffs that are that constrain these ages. We can, they date to about 635 million years ago.
So this name
there was this,
is this just the term that's used for this glaciation event, this given glaciation event that's occurring at both poles?
well, this is occurring everywhere. This is not so these early ones, 635 million years ago. These are called Snowball Earth events. So this is runaway glaciation.
So this is okay. So this is Precambrian. This is
yes.
Oh wow. Okay, I was way off. I was imagining that this is like more recent glaciation. So this is Ediacaran and earlier
Exactly.
glaciation.
Yeah.
That's wild.
Yeah. So you've got these, but you've got these unmistakable glacial deposits, and they're overlain by carbonaceous capstone.
Right.
You get the glaciation, and in order to get rid of the glaciation, you have to drive up the carbon dioxide levels, which the volcanoes do eventually. But as soon as that happens, you start sucking carbon dioxide into the ocean. So you get this carbonaceous capstone, these cap dollar stones as they're called. So you tend to get tens of meters of these carbonaceous dollar stones, and there's a question there about how quickly they can form, because you need the carbon dioxide to be absorbed into the ocean, transferred to the deep ocean, and then deposited. But if that's but you need at the same time to keep the ocean sufficiently non-acidic that life can exist there. So there's a cap on how quickly you can suck that carbon dioxide out of the air and form this capstone and not kill everything in the ocean. Because if you pull it out too quickly, you're going to just kill everything. So
I could see them attempting to explain sort of the snowball Earths in a couple of different ways. I mean, they would likely suggest that this is either occurring before there was life at all, or very early in the creation week, which would be strange because we know that life existed at this time. We can track their signals in the rock as well. Or they would suggest that this is something that occurred during the flood. Those are their only two options, because obviously, even in the pre-flood world, as you mentioned, your tubal canes might notice, a worldwide glaciation that, basically touched in the middle at the equator. So,
yep.
And what's strange to me is that obviously they can't, at least I would have a hard time imagining that they could write this off and fit this in their model as just, oh, it didn't actually happen, because the signals for glaciation are, of course, and the uniformitarian principle or actualistic principle would state that those glaciation signals should look like the ones that we see, at least today, in a much larger form. And I imagine that they do, right? That it's standard, like the same type of glaciation that we see today, because the process of glaciation it's the same every time. So the glaciation that we see today should be a much smaller version of what we see 600 million years ago. Is that the case?
Yes, that's the case. So, and if they want to make it a pre-flood event, then they've still got their problem about how do you build a globe, a snowball Earth, if you've got a gigantic geothermal signal. So if you've got this massive heat flux from below that's coming up because the continental plates are running around all over the place, how do you build an ice sheet? Because in order to get a large ice sheet, you need a very strong bond between the ice and the underlying bedrock. If the ice is too weak, it'll just slide away under its own weight. If the bedrock is too weak, then it'll get bulldozed aside by the ice. Basically, the weight of the ice is trying to slide away, and the only thing that can stop is a strong bond between the ice sheet and the bedrock. So if you've got this huge geothermal signal that's just heat's coming up from below, you can't build these large ice sheets. They won't accumulate. They'll just fall over and refuse to get any thicker.
Right. So this can't, okay, so that makes it, given our continents would have to be zooming around at race car speeds in the middle of the flood because of this catastrophic plate tectonics idea, or hydroplate, it doesn't matter. They have to move around very quickly regardless. And depending on who you're talking to, they're potentially going from Pangaea to now, or they're potentially going from an ancient spread out continental arrangement to Rodinia, to to Pangaea effectively, and then to now. So and every intermittent stage as well. So what you're proposing then is that this has to be in the pre-flood world, and it also can't be that because we're talking about a process that's taking hundreds of millions or hundreds of thousands rather of years to come, to arrive, and then to retreat.
Yes, that's right. In order to get enough carbon dioxide into the atmosphere to make these things, to dispel these ice sheets, is a slow process because volcanoes don't produce carbon dioxide that quickly in general. Now, that may offer some sort of scope for young Earth creationists to claim. Well, maybe there's a lot of volcanism because there's everything's whizzing around so fast. But that still doesn't explain how you get your multiple phases. This has happened multiple times, and you've got kilometers thick glacial erosion. How do you get kilometer thick layers of glacial debris in a week? You can't, right? You cannot move the ice that fast. There's a reason we refer to glacial slowness. You can't move the ice that fast because if you make the ice sheets thicker and thicker and thicker, then they'll just fall apart. They'll overwhelm that basal shear stress. Right? There's a threshold stress, and once you exceed it, the ice sheet no longer bulldozes; it falls over.
Right.
So you can't just make it heavier and heavier and heavier and expect it to do the work. That won't work. You can't make the rock weak, because if the rock's weak, then it'll just get easily sloshed aside and you won't get a large ice sheet. If there's, you can't make the ice, you can't lubricate the ice so it will move faster, again, because that'll just result in no erosion, because the ice sheet will collapse. You cannot do it quickly. So how do you generate, 1,500 meter thick layers of glacial debris on multiple occasions in your pre-flood timeline? When does that happen?
Right.
And if you're a young Earth creationist, it's your obligation to explain the data. This is the observational data we have. You explain it. So there doesn't seem to be any way. And I mean, these formations are huge. Like as I'm saying, they're hundreds of meters thick of glacial, but then they've got at least as much or more material accumulating on top of them.
Right.
So and that's the other.
Yeah, I wanted to ask you, because I'm trying to imagine, like, with these massive deposits, like you utilize things like radiometric dating to get dates from different sections of these glaciers, right? Of these ancient glacial deposits. But what is the deposit itself that we're looking at? Like, what is it actually composed of? So what happens is that the glaciers, they grind up the bedrock into very fine dust, and that gets put out as this very fine silty mud. But then we're talking about a combination of till and what are called diamictites. And diamictites are a glacial deposit that forms when this very fine-grained silty mud is deposited in a marine environment at the edge of a large ice sheet. And what happens is that some of the rocks that have been picked up by the glacier, they get let loose as what's called ice-rafted debris. So basically there are icebergs that contain these hunks of rock, and they drop them into the mud. So you get these. Drop stone?
Yes, that's a drop stone, exactly. So you get these drop stones that have dropped into this finely sorted, fine-grained mud, and so they stand out. They have a very unique look and composition to them. So yeah.
Awesome. Cool. So this idea then that, we've got to fit massive amounts of glaciation just from the Precambrian at some point into this pre-flood world, which from a young Earth creationist perspective would be somewhere between 6,000 and 4,400 years ago. Or they can just cram it into the creation week and say they've got one day to do hundreds of thousands of years of glaciation in multiple pulses. Because as far as I'm concerned, there isn't a young Earth creationist out there, and maybe there is, and I've just not met them, who doesn't consider Precambrian rock or like basement granite rock to be like creation week rock. So
okay. Well, in which case they've got a significant problem,
right.
Because we can detect large scale erosion deposition, and this is the other pincer, I think, of cosmogenic dating. Because for instance, there's a 10-kilometer thick layer of sediment in the Bay of Bengal, northern Bay of Bengal. According to the creationist timeline, this must all have been deposited very, very quickly. As a result of which, there must have been a lot of erosion in that catchment area. So we can go through and we can do cosmogenic exposure age testing. And if the young Earth creationist hypothesis is correct, we should get no old cosmogenic exposure ages because they simply haven't had enough time to be exposed to cosmic rays.
Right.
So, but when we do that, that's not what we see. We see that they have ages of hundreds of thousands of years. So there is no evidence to support a massively fast erosion event in this region.
Well, and cosmogenic ray exposure is something that, to me, like, okay, take radioactive decay, right? This is something that at least they can say this is a process of decay. It's not exposure to something else. It's a process of decay. So we can at least say, whether it's magic or not, that the process was sped up. But when it comes to cosmogenic ray exposure, I can't even think of it because it's not a mechanism. It's exposure to something else. So I don't know how you would speed up exposure to the sun.
No, it's not exposure to the sun, and the vast majority of these are actually extrasolar. So they're from outside the solar system. A lot of them, in fact, are extragalactic. So they're
but is it still radiation?
So they're high energy particles coming from remote sources. So and it's actually, but there's but again, so they can they say, well, just speed it up, just speed up the rate at which this stuff is entering the atmosphere. And there are a couple of major problems with that. For starters, everything would have the same cosmogenic exposure age, right? Anything that, as soon as you ramped it up, everything would have the same age from that perspective. But there's also the other pincer of this, which is cosmic ray impacts are what generate carbon-14.
Oh no!
So if you vastly increase the amount of cosmic rays entering Earth's atmosphere, then you should have massively vast carbon-14 deposits that haven't yet had time to undergo any significant radioactive decay whatsoever. And so you need the carbon-14 to have undergone some different process from the other radiometric isotopes.
Right.
So you're basically you're basically shooting yourself in the foot. But let's look at the Grand Canyon. So there have been cosmogenic exposure age studies done on the Grand Canyon. Is that, if we've got two hypotheses, one is the Young Earth Creationist hypothesis that the canyon walls were created virtually instantaneously, and the other one is that this was a gradual process.
Right.
Now, in the one case, they should have the exact same cosmogenic exposure ages, right? You went from the top to the bottom inside a week. How much can cosmogenic exposure change inside a week? And everything else would have to have that age, the age of that wall. But that's not what you observe. You observe that that the top is 8 to 10 million years old, I think, and and at the bottom you're talking 1 to 2 million years. You're getting about they use this to constrain the incision rate. So you get an average incision rate of 170 meters per million years at the site that I saw studied. I can give you the citation for that later on if you want. But
sure.
But
I just later, what we'll do is at the end, sort of after we finish here, whatever citations you want me to provide in the description, I'd love to stick them in there, just because people, some folks like to get a little deeper and go to the source of the source, right? Yeah, so that's something that I'd not considered, though. I mean, so one of my favorite examples for the age of the Earth being quite ancient is, as you've seen this probably on the channel, but using the Mid-Atlantic Ridge. So you've basically got the movement of the continents, which is corroborating radiometric dates along from the distance of the Mid-Atlantic Ridge where seafloor spreading is occurring. And these two things are of course entirely independent. The rate at which the continents move and radioactive decay would have to have been sped up during the flood like stepwise clockwork just to appear to corroborate one another. But now it seems like you have to add another completely independent cog to this machine that is sped up in stepwise process, and that's that cosmogenic ray bombardment. Because this is, as you mentioned, and I was under the impression that this was from the sun, but this is stuff coming from deep space, as you mentioned in some cases. So that has somewhere in the bowels of the solar, or of the galaxy, we've got to be emitting these particles that are effectively reaching Earth and bombarding substrates on the Earth, to give the appearance of ancient ages that just happen to corroborate radioactive decay on the Earth and the movement of the continents.
Yeah,
that's pretty bonkers.
Yeah, and I think that it's just they don't know that these dating techniques exist, and they don't know what.
You're right on that.
They're focused on this radiometric stuff, and they don't understand that we could throw out every radiometric date we've got. There's no basis on which to do that, but we've still got other dating techniques,
right?
And they do not. None of them admit a young Earth creationist timeline, and these other dating techniques work on completely different physical principles.
Right.
Carbon-14 and a couple of the other cosmogenic isotope, they are sort of composites. So you can the impact of these cosmic rays creates these exotic isotopes that then undergo radioactive decay, like carbon-14, beryllium-10, aluminium-26. But there are a couple that don't undergo radioactive decay that just sit there inert. Neon-21 and helium-3. So we can measure those abundances, and you can throw all the criticisms you want at radiometry. This is a different physical principle. This is the amount of cosmic ray incidence that has occurred, and what time frame, and how long has it been exposed to it, and also how much erosion has occurred. How quickly can erosion have occurred in order for these cosmic ray accumulations to still be present in these bedrock surfaces and rock surfaces. So the thing is, if you sort of scrape away that top layer, these cosmic rays don't penetrate very deep into rock. So if you scrape away that top layer, it's fresh. It should show a cosmic exposure age of 0 after 2 meters. So there's a limit to how fast these processes can all occur.
Wow, that's rough.
Well, it's also rough if you look at the ice core data. For instance, from the Antarctic, which has the longest ice core record, and we're trying to currently extend it by digging deeper. But you can see dust. You can work out how many dust particles there are per layer in that. Now, if the young Earth creationist hypothesis is correct, then as you go deeper in the core, there should be less dust, because those less dust per layer, because those layers were formed more quickly. So there's less opportunity for dust to get in there.
Right.
But that's not what you see. Similarly for ocean cores, you find these tiny organisms called forams or foraminifera in there. And if you go, and as you go deeper, you should expect, if these sediments were deposited quickly, that there would be a lower abundance of forams as you go deeper, because those sediments were deposited extremely rapidly. So the rate of forams per sediment layer should be smaller, but that's not what you see.
To both of those points, I have something to say about them, because I think I can at least add to what comes to my mind at first, an additional problem. With the dust, especially this is more to do with areas in the north, around the North Pole, so Iceland and Greenland and places like that, where there's a lot of volcanic activity. But these volcanoes in the very recent past 100,000 years, 160,000 years odd, they're going off periodically, and the dust and ash from those guys are getting sealed in between these layers. So if a lot of these, layers were deposited quickly, these, ice layers, because they often like to point to these weird, funky examples of snowfall occurring very quickly, and like World War II planes and crazy stuff like, I'm sure you've heard of it, to be like, well, these ice layers could be deposited quickly. Oh, really? That's interesting. So if this is being deposited, during the course of a day, when we're saying it signals 50,000 years, let's just say, for the sake of it, right? Then every volcanic eruption that occurred in conventional science is 50,000 years, just erupted during that single day and deposited its signal respectively throughout this layer that was supposed to be, a single day's deposition, which is of course absurd. And with the forams, that's one that I know very well, because biomass of planktonic organisms is very large in today's oceans. So if you were to say that every single layer from the Cambrian to the Cretaceous was deposited during a single global flood, then you have to say that every single sampling of forams in this case was basically living contemporaneously during a year period, because they reproduce pretty quickly, but they don't reproduce quickly enough to give the illusion of, what is effectively almost 400 million years of time. And so the biomass of all that plankton would effectively turn the ocean into an amoebic sea. It would be a sludge of microscopic life if you're saying that every single foram that we had lived during the time period of a year instead of 400 million odd years. That's insane. It's insane.
Yes, exactly. And also to explain, in order to explain, so you're looking, if you're trying to, compress 400 million years into 1,000, say, you've got 5 orders of magnitude. Okay. And that's crippling. But if you're trying to do it into a year, obviously it's even higher, but let's stick with the 5 orders of magnitude. But in order to explain the dust example, you're trying to, you need the winds to be creating dust and transporting dust 5 orders of magnitude faster than winds currently do that. And you need to do that without anybody responsible for the biblical narratives commenting, well, it was a bit windy back then too.
Right.
We did notice that birds weren't as keen on flying as they used to be, because so there's a lot of and again, in order, so can you really increase average wind speed on the Earth by 5 orders of magnitude and just expect that's not going to show up for avians or insects or anything. That's not going to impact their migration paths, their lifespans. You've got so many moving parts, and they're all interconnected. And wherever Young Earth Creation attempts to fit into a scientific narrative, it just cannot do it.
Yeah, well, something that you've done in this conversation that I appreciate too is that, we're talking about the issues with things, with deposition of these kinds of signals in the case of the ice cores and the forams during the flood, and in the case of the glaciers, the glacial deposits, and, the dust that's, within them, both prior and after the flood when humans are around. So there's an issue for it at every single stage. It's not just, we're not just talking flood issues or pre-flood issues or post-flood issues. It's every single stage. There's a massive problem with these interconnecting signals, as you mentioned, all in lockstep breaking physics just to give the appearance that the Earth is ticking away at its normal time and minding its business and responding to normal pressures.
Yeah. So returning to the carbon-14, if you're going to explain away the carbon-14, then carbon-14 needs to be affected by whatever magic you're doing in a different way from aluminium-26 or a different way from uranium-235. They cannot be, if they were affected the same way by the same miracle, then we would then you actually have to increase all of the carbon-14 ages. You need carbon-14 to be extincted, to undergo radioactive decay much, much faster than all of these other species, because you're creating it much more rapidly. So, it just presents to my mind an insurmountable problem. So you're making what is already miraculous need to be vastly more miraculous in order to support your position.
It's all very unnecessarily convoluted, in my opinion. You know what I mean? It's because instead of just the Young Earth Creationists, instead of just saying, okay, it just looks old, right? Like they're just, instead of just taking the position that it all just looks old, it was created to look old, that's fine. They have to invoke these weird processes in order to not make God's nature deceptive, which is a theological issue that they face. And they have to do it in such a way with the carbon-14 that you mentioned, so as to not lose the corroboration that they so desperately cherish, right? In the case of the Dead Sea Scrolls or other, places where they like carbon-14 dating and how it works. So they have to say, it works just like it should up until about 6,000 years ago, and then it just stops. It just completely breaks in every possible way, and forget about even trying to use it. Which is what? What's the mechanism? What do you mean it just stops working, and only in the way that just appears? I mean, golly, the more you parse out the minutia of literally any field that has to do with the age of the Earth or biology, you run into snafu after snafu after snafu.
Yeah. And actually, this is where I might like to introduce some of the slides that I put together.
Please.
Actually, the story of this starts with Anders Celsius. It's an interesting little anecdote, but perhaps takes up too much time. He just noticed that there were these valuable pieces of real estate called seal rocks, where seals would come out of the sea, sit on the rocks, and sun themselves. And they were quite valuable because hunters would own them. So hunters would buy them and own them and hand them down as heirlooms. And he noticed that they had a finite time limit. This was, on the top there, you see this rock that he identified that was 5 foot out of the water in his time, and it's now significantly above water. And so he went and carved his initials and the date 1731 in that rock in the lower left. But it's not exactly mysterious that in some locations in the Earth, sea level has been falling. You can see the succession of shorelines that form very, very, there's just a lot of them in quick succession. And again, the question is, how quickly can these indicators form? You're requiring a lot of erosion, creation of sand, deposition of sand. That one's from Sweden. The other three were from Canada. Actually, there was an American geologist who worked out while studying. What's the name? The Lake Bonneville. He worked out that the paleo shorelines for Lake Bonneville were tilted, and consistently they were tilted towards centers of glaciation. And he applied the term isostatic, and we see It's not what I wanted to do. Anyway, so we now have this theory that relates mass exchanges between the ice sheets and the oceans with this geophysical process, the flow of mantle material, deformation of the crust, changes in gravitational attraction, and rotation. So using this, we can combine sort of data on where these glacial erosion features are seen. This is a Landsat image on the left here with the sea level data. Now, one of the problems is that these glacial erosion features, you can find multiple edges for the ice sheet. And in Fennoscandia, this is one potential configuration, and this is another potential configuration. Which one is right, or when was the ice sheet? And obviously they're both right. That's the evidence we have. But when did this occur? And it turns out that we can look at the sea level curves from different locations, and these are from Scandinavia, obviously. And here, for instance, in Angerman, you can see this almost beautifully exponential sea level fall. Carry on.
Yeah. No. I'm looking. I was like, you're right. Each time it's got that nice kind of exponential decrease, or it looks like a decrease from where I'm at. So. Yeah.
But again, if there was some error in our chronology, then these wouldn't look right. If there was just random errors associated with our geochronological techniques, then these curves would not have coherent patterns. As you move towards the edge, you start seeing more interesting patterns. Increases, decreases, rises and falls. And you start seeing sea level signals from earlier in the process, because these are the areas that were deglaciated earlier, and so on. Well, so sea level indicators had an opportunity to form, and one of these is from near the glacier, but the other two, Store Belt and the North Sea, they're from further out.
Right.
And you can see that in this case, sea level rose, and it rose up smoothly towards zero. So you've got this geographical distribution of sea level signals. You've got this geographical distribution of ice sheet indicators, and you try and put them, and you've got a theory for how they're connected, and you can do sort of regional reconstructions like we've done here. These papers all come from my group, so I'm biased. Sue me. There's another aspect to this. So we've seen, you need time for these sea level indicators to form, but it's not just sea level indicators. These are from Fort Severn, Ontario. You see again these successions of beaches having formed, but these aren't sea. These aren't the ocean. These aren't ocean shorelines. These are actually lake shorelines.
Okay.
So the gigantic ice sheet that existed dammed the river systems, and this is a hypothetical reconstruction of what they might have looked like. You can see sort of broad lakes. At the top left there is Lake Mackenzie moving. You've also got the Great Lakes starting to fill, and then you've got in between them sort of Lake Agassiz. But I wouldn't get too obsessed with the details of this. There are a lot of uncertainties about sedimentation and paleotopography.
But the
sort of make these
the lakes are pulsing in time with the way that the sea level is rising and falling due to the glaciers.
Well, as the glacier recedes, also as the land deforms, and as the gravitational, there's a gravitational attraction component to all of this. So the mass in the ice sheet, just jumping quickly back to this original cartoon, you can see that the water is piled up towards the ice sheet because the mass in the ice sheet is actually attracting the water in the ocean basins towards it. And so if you melt a near glacial ice sheet, actually the loss in gravitational attraction is always bigger than the amount of water that you've added to the oceans, always. So you'll actually sea level fall near these ice sheets, and the same is true of lakes. And in fact, the tilts on these lakes, like the tilt on Lake Bonaparte, is influenced by the gravitational signal. So we can tell, for instance, that that this eastern section, the Laurentide, was quite big, and the western section, the Cordilleran, which you can see over there with its own isolated little red star, that was very, very small because the gravitational signal of the ice sheet on the Laurentide ice sheet is much bigger. It tilts the water towards that ice sheet. But as these gravitational and deformational signals evolve, and as the mass of the ice sheet evolves, you get these different shorelines being formed. And again, that indicates that this ice sheet must have been present long enough for these lake shoreline, for this quite substantial succession of lake shorelines. There are 50 or 60 in this photo alone. The ice sheet must have been there through all of these formations, and it must have been there long enough for each of these formations to develop. So that's that would seem to conflict with the Young Earth Creationist timeline. We can go further afield and we can look at, for instance, northwest Australia, where we've got this depression on the continental shelf, and this is what we think it should have looked like at about 20,000 years ago, using our best topographic and sea level models. So we developed the theory: if we send an ocean drilling mission there, it should be able to find evidence of sea level change. It should be able to find transitions from a freshwater environment to a brackish environment to a saline environment. And when we did that, that's exactly what we saw.
I'm shocked.
And as you can see in the table on the left, we were able to get dates for these that were coherent. So we could get dates for these transitions from freshwater to saltwater environments that make sense. So we can take a global compilation of these sea level indicators, put them together, and this is approximately what global sea level in a mean sense, average sea level across the oceans, has done for the past 30,000 years ago. The further you go back, the less data there is. Unfortunately, that's just the way it is. So as you go back, there's more and more uncertainty over what might have happened. But certainly for the past 15,000 years, we're on fairly solid ground as far as that. And now we can return to the question we had earlier, and we can say that this configuration was what happened 20,000 years ago. And the reason it can't have been, the Fennoscandian ice sheet can't have been this big 20,000 years ago is that it would have taken more water out of the oceans than allow. So we can now say that this is an older environment, and we have sea level indicators from this past, the penultimate glacial maximum 140,000 years ago. Anyway, so we can do a reconstruction of global sea level change since 20,000 years ago, and we can put the ice sheets on top of it, and you can see that things are very different. You can walk to places you can't now walk to, and you can go and test stuff. And this is where we start to get into sort of some of the stuff. For instance, hominin migration out of Africa. One of the proposed points has been, the shallowest point in the in the Red Sea.
Yeah.
And that's marked here with a black star. This is called the Hanish Sill. But we did reconstructions of this, and that would involve crossing 8 kilometres of open water. Now, the water's only about 13 metres deep on average out there, but you can see these islands, the Haycock Islands, down south of this, and they provide a much more convenient route and a much more visible route. You're always in sight of land as you make these island jumping. So if we were to suggest where you might look for evidence of hominins coming out of, crossing this stretch of water, we would say that, leapfrogging the Haycock Islands would be the best way to go. It's certainly a much more convenient route than the Hanish Sill.
What did you say
going back to
the timeline we're looking at here is?
This was 20,000 years ago. So on longer time scales, these would be, these would be modern humans.
Right, exactly.
On longer time scales, there are tectonic uncertainties that would impact this reconstruction. So, before 500,000 years ago, tectonics might have just left this route completely open during glacial. We don't really have enough data to do anything. We don't have enough data on the tectonic component of this to do reconstructions this detailed. But also, you don't get this result if you remember that average sea level curve I showed you?
Yeah.
If you just apply that to the topography, you get the wrong result. Right? If you use that, as many researchers have done, you can see that the change in sea level here is only of the order of 110 metres, not the 135 metres of the mean sea level. So applying mean sea level is a bad estimate in a lot of if you applied mean sea level, you would conclude that everybody could just walk across and there would be no problems.
Right.
But actually, that's not the situation. The situation is that Red Sea was connected to the oceans at this time. We can prove it with multiple lines of evidence. While the channel was very, very narrow, it was still there. So there would have been some water crossing. But if they'd gone via the Haycock Islands, the maximum water crossing would have been much shorter, would have been less than half what it would be at the Hanish Sill. So this is another nifty example, I think, from southern France, where these caves were discovered, the Cosca cave, which the entrance is now 37 metres underwater.
Right. It used to be.
But it used not to be. But inside you find these very spectacular cave paintings.
Yeah.
Now, if these were post-flood, they'd have been destroyed.
Right.
Right. The flood would have destroyed these paintings. So if these were pre-flood, they would have been destroyed by the flood. So these must be. Sorry, I was getting it back to front.
No, I was right along with you. I was too busy looking at them. So
these are clearly post-flood, and the question is, but they date from a time when the glaciation was, when the Earth was still glaciated, when sea levels were at least 40 meters lower than they are now. So how did Noah's descendants get from the Middle East to here so quickly? What is their model of population growth? especially since they require the end of these glaciers to be very, very rapid. Where else?
And that would have to correspond too with these signals that you're discussing, right? I mean, this had to have been like basically immediately after the flood if they're going to claim that the sea levels were, I guess low at their low point in comparison to now. So they've got to like hustle down there, get into the cave, make the cave paintings, all before we start seeing the registration of sea levels beginning to kind of move to their current position.
Yeah, exactly. Yeah. So there's a very real problem there.
I would say so. Yeah.
Now I'm going to turn to the ice core data. This is the ice core data that we've got. That red box indicates the approximate limit of our VAV chronologies and dendrochronology data. So the ice core data goes back much further than these other records, but where those other records exist, the agreement between them is extremely good. So here's a sample of agreement between dendrochronology, VAV chronology, speleothem chronology, and ice core data.
Wow, that is a beautiful graphic.
Yeah, so you can cross-check them by looking at the cosmogenic isotope abundances.
That's fantastic.
Yeah, so these are so we can tell that where they overlap, these records agree, but the ice core records go back much further. You can see in sort of brown there the dust records, which, as I say, they don't show any diminution in magnitude. Now, up the top, you can see the isotope ratios, the oxygen 18, the ratio of oxygen 18 to oxygen 16, and the ratio of deuterium to normal hydrogen, so hydrogen 2 to hydrogen 1. And you can see that they vary in sync. Now, what's happening in that, and I would also point out this curve down the bottom labeled benthic, which seems to show at first glance the same sort of general agreement with those isotopic records above, but it should be noted that the scale is reversed. So this is a decreasing scale, and that's an increasing scale. And what does this graph show? Well, it shows the oxygen isotope ratios in 4ams. This is an example of a list of 4ams that we find in ocean cores. So, what's going on is explained in the cartoon in the lower left. So you've got your ocean. The water that leaves the ocean, heavy water that contains heavier isotopes, oxygen 18 or deuterium, it's less likely to evaporate. So those clouds are depleted in these heavy isotopes. And as they progress towards the ice sheet, the heavier isotopes tend to fall out and rain. And so by the time they reach the ice sheet and drop their water, it's extremely depleted. And the ocean is correspondingly enriched in these heavy isotopes. And that's why these isotope signals for the ocean and the ice sheets are in the opposite sense. That's why those scales are reversed. The more massive the ice sheets and the colder it is, the more enriched in heavy isotopes the ocean is, and the more depleted in heavy isotopes the ice sheets are. So sort of this is a proxy that we can use. And you can, on the right there, you can see these are just oxygen isotope ratios, heavy oxygen versus light oxygen, going back as a function of time from 57 different cores from around the globe. These cores are widely spaced.
So you've got a nice range of samples there for sure.
So, but they agree, right? You can see that they agree.
So they're convening in on the status of the ocean. the oceans and the seas.
Yes.
Not just the oceans and the seas at a given point. They're converging on this single picture.
Yep. So this picture is so here's what you get when you coalesce these when you coalesce all of these different oxygen isotope records, and this is where the marine isotope stages get their nomenclature from, is these numbers and timings here. Now that red square, rectangle, whatever. It portions off the length of the record that is covered by the ice core data. So the ice core data is vastly longer than the dendrochronology data, and this marine isotope data goes back much, much further. Now you can ignore the ages down the bottom if you're a young Earth creationist, because they rely on assumptions about sedimentation rate and various other things. So you're not on. These are not. The author's intention was that the actual timings of these could be perfected as we got more data. So they weren't using any radiogenic. My apologies.
No, don't worry about it.
But it's worth noting down at the bottom are the magnetic reversals, right? And these are recorded in these. So you've got the various stages of magnetic reversal going back, and this covers only, we know of at least 300 magnetic reversals, but these marine isotope data only covers, a couple of dozen at best. It's
so measuring magnetic reversals. Just as a quick aside for those who maybe don't know who eventually will see this, how do we tell that a magnetic reversal has occurred?
So there are a number of ways you can do it. One is you can look at the rocks,
right.
And you can look at crystal alignments in rocks,
right? Like iron, things like that, with their poles. Yeah. Okay.
Yeah, that's right. The other thing you can also do it in sediments as well. So you can measure because of the way sediments deposit themselves in a in a watery environment. There are statistical properties of those those grain alignments that are similarly sensitive to what's going on with the magnetic field. So you can actually directly observe these magnetic field reversals in these sediments themselves.
Yeah,
so this is not an external data set. This is an internal data set from the marine cores. So these, and obviously, we take the magnetic reversals from these cores, and we correlate them from the magnetic reversals observed on the ocean floor. As the ocean floor spreads, the magnetic polarity is recorded in the grains. One of the things that I did want to quickly touch on, because I'm already aware that I'm taking up a lot of time, is sometimes you get these marine terraces, like these ones are from California, and you can see they form a succession. And when you date the higher terraces, they're older than the lower terraces, and you can see very clearly that these have undergone much different erosion processes than these early terraces that we were looking at, right? So there's much more a sort of wind-driven, wind-driven erosion, much more vegetation, so these are clearly of a different epoch, and indeed, these represent the ages of these correspond to these different isotopic stages going back in time. So that starting from sea level on your left there, that first one is the last interglacial,
right?
MIS 5, and then you go back to MIS 7 and MIS 9. So these go back in sequence. But if we look here at Huon Peninsula, which is a very rapidly uplifting area, actually these terraces are not in chronological order, because the rate of uplift of the terraces is of a sufficient magnitude that a shoreline that is formed at a sea level minimum will actually be more uplifted than a sea level that is formed. So these aren't in chronological order,
right.
And indeed it takes quite a bit of sort of unraveling
right.
to work it all out.
Right, you got to diagnose all the rocks. How they're moving. Well, what types of rocks are in accordance with how the uplift is impacting them.
Well, most of these are coral terraces. So, so these reefs, these are just reefs here.
Right.
What you're seeing is the emergence of coral reefs and their uplift. So, but you also see coral reefs growing. You can see young coral reefs growing on older coral reefs, which are themselves older than the coral reefs above them and below them. So there's a lot of intricate untangling that needs to do. This gets back to this diamictite thing that we were talking about earlier. This is the early glaciation. So this is just an illustration of sort of these large stones falling into this finely silted mud. See the carbonaceous capstone on top. And indeed, this is a collection from around the world. So, you can see the scale of these formations, that keel formation. Yeah, so they're absolutely, so the scale of these events and the time scales needed to construct them. Down on the bottom right, you can see that thin layer of white capped dolostone is more than 10 meters thick, and it's overlaid by glacial sand wedges and diamictites. Again, the same you can see in the Svalbard picture, 22 meters of carbonaceous capstone on top of this massive layer of diamictite. And if we look at and here's the Oman case, and you put another red rectangle around the scale. That black line is 500 meters, so you can see that there are multiple. Their combined thickness is about 2 kilometers, but it's in multiple stages.
Wow, that's impressive.
Yeah, so just the evidence we have just doesn't agree with the young Earth hypothesis. It's not a matter of what we believe. It's not a matter of what we would like to believe or like to deny. It's just a matter of the data. The data just doesn't let us. These processes cannot have occurred as quickly as young Earth creationists occur, and until they can demonstrate that such a thing is possible with some independent form of evidence, they can be content with their claims being laughed out of every reputable scientific journal on the face of the planet.
I couldn't have ended it better myself. I think that's perfect. Tony, thank you so much for taking the time with us today. I really, really appreciate it. This was an absolute delight.
Okay. Well, I'm sorry I prattled on a bit long, monopolizing.
Oh my gosh, no, I was just trying to soak it in. It's, for me, since this is geology, I have geologists on the channel as often as I can. But it does take me a minute. I usually have to watch these things a couple times before it really sinks in for me, because this is such, it's such a new field for me to understand. So usually I'm like, okay, I'm following along, but if it were up to me, I'd be taking notes the whole time. But I like to try to first watch, I like to try to just soak in as much as I can and then rewatch it later. Yeah, plug it for us. Tell us where it's at.
It's just under the name PhD Tony.
Perfect.
I started out doing some flat Earth debunking because that's even more ridiculous. But also got some geochronology presentations and some climate denialism presentations, because I think that they're the big three forms of science denialism that we need to slap down at the moment. And if you're a climate denialist, you don't think you're on a par with a young Earth creationist, that's just because you don't know what you're talking about. So that's my channel. I'm told I'm really boring, so we'll see how it goes.
No way. If you find it boring, you're just not into the subject, because I thought this was riveting.
Well, I will make a note of etiquette for you. Never call a geologist a geophysicist, or vice versa.
That's good to know.
The two groups loathe one another with the white-hot intensity of 1,000 suns.
No.
I don't know why, but there's I have to admit I don't know much geology. That's okay. And geologists are useful sometimes, I guess. Yeah.
Well, here and there. I'm kidding, all my geology buddies. I'm kidding.